Let's get some practice analyzing some IR data here. We have a spectrum over here, and we have just some word data for our second problem. So let's look at the first problem. We're given the molar mass of 68 grams per mole, and we're going to use molar masses with sig figs of about 2 in this section. So we're not going to get too detailed, but we can add up carbons that weigh 12 and hydrogens that weigh 1 and so forth. So that's going to be helpful. And then we have our IR data. And again, we have the lines that we're supposed to draw on the spectrum here to try to find interesting peaks. There's really nothing in the double bond region, but I think this is pretty indicative of a triple bond, and that's likely a CC triple bond. Given no other information, that's a good place to start. And so there's either a possibility of having carbons on either side of that, or having a hydrogen on one side. And so we should look for potential stretch of that CH bond on an sp hybridized carbon. And if we look in the table in the book, that type of bond is found at around 3300 in our XH bond region. So 3300 is right here, and you can see there's a nice sharp peak. So that's pretty indicative of a CH bond on a terminal alkyne. So now I know that I have a triple bond and I have an H on the end of it. So let me erase what I have here and start over a little more cleanly. I've got an H, I've got a triple bond, and then I've got some more carbons and hydrogens that add up to 68 grams per mole. How can I get to 68 grams per mole? Well, I know that C's are equal to 12 grams per mole, and so if I have 4 of them, I have 48. That would mean I need 20 hydrogens, and that's impossible to have with 4 carbons. So what about 5 carbons? 5 C's equals 60 grams per mole. That's pretty close to 68, so maybe I have C5H8. Is that a reasonable formula? Well, we can calculate the HDI, and again, that's going to be 2 times the number of carbons, plus 2 minus the number of hydrogens, all divided by 2. That gives me 10 plus 2 is 12 minus 8 is 4. 4 over 2 equals 2 HDI, and that would be accounted for in this triple bond. So I think that's a pretty reasonable formula. That means I need to add 3 more carbons and the right number of hydrogens now. And if I count what I have 1 H, 2 more is 3, 2 more is 5, 3 more is 8, 1, 2, 3, 4, 5 carbons. That matches the formula. So most likely, this is my molecule that corresponds to this spectrum. Let's look at the other problem here. It's a word problem. It says propose all possible structures for a compound with formula C4H8O. And right there we can stop and calculate the HDI. 2 times the number of carbons plus 2 minus the number of hydrogens, ignoring the oxygens. There are no halogens or nitrogens, so we can just divide this by 2. That's 8 plus 2 minus 8. 2 over 2 equals 1, so I should have a ring or a double bond in this structure. Another clue is the broad signal between 3200 and 3600. That is probably an OH group. That accounts for the oxygen. And importantly, it does not contain any signals between 1600 and 1850. So that means I have no double bonds. That's another good clue, because I know that I have an HDI of 1. I need a double bond or a ring. I must have a ring. So let's draw a ring. I could draw a 4-membered ring because I have 4 carbons, and I could draw the OH. And now I should decide if I can draw other sizes of rings. I can certainly draw a 3-membered ring, have an extra carbon, and the OH. I can draw a 3-membered ring. That's supposed to be 3, extra carbon, OH. And I can keep drawing this 3-membered ring until I can't Can't make any more combinations. I think I have these 3 combinations. That's all I can draw. As far as the 4-membered ring goes, that's about all I can do. One could argue for a 5-membered ring, including the oxygen, but I think we can rule that out because we know there's an OH group in this molecule. There is no OH group in this 5-membered ring with an oxygen. So I think I have the 4 possible structures. We cannot narrow it down any further with just the data we have. So these are all possible structures given this data, and we need more data, maybe from the NMR spectrometer, in order to narrow our search for the correct molecule even further.